Hello, everyone. Welcome again to week two of your lectures in APM 2A. So I'm sure you met Dr. Visaya last week, and this week you are with me. We are co-teaching this course. You are with Dr. Chirovi, and this is my second time to teach together with Dr. Visaya, so we have been teaching together for some time now, and we hope you will benefit from the expertise that we have. All right, so I can see people are trickling in, and we will get to um, others will join on the way. So let's start right away. So if you have been checking your emails, I sent an email yesterday telling you about what we are covering this week and the tutorial questions where you find them on the blackboard. And today I sent you a message saying the notes are now uploaded. Please go through them, and we are going to basically focus on the major points that are points of emphasis in as far as understanding the material for this week. So basically, we are looking at direction fields and some methods of solving differential equations, the first order, and the particular method called the separation of variables. All right, and of course, when we do that, for us to have solutions, we need to make sure that the solutions exist in a certain specific domain of definition. So that's what we are going to do. So whatever we're going to do here is just points of emphasis of what the notes are explaining, and you will find that some of the examples that I use in this emphasis are not necessarily the ones that are in the notes, which is okay, because then it means you have more than one examples that you now know about that's a specific concept, and then you understand better as well. All right, so let's start off with direction fields. So last week you were basically dealing with the introduction part where you focused on the different definitions of differential equations. Okay, all right. So JV, can we shelve that question towards the end after I have gone through what we are doing today? So I'll answer it. Don't worry, I'll answer it, and at the end of the day, you will be happy. So you were talking about definitions of differential equations. You went on to classify them with the type, the ODE or the PDE, and then you went on to type according to order, according to linearity, and so forth and so forth. And hence we have a question here. I will answer this question towards the end. Please remind me, JV. Don't if I get carried away, please just remind me that I need to answer your question, but I will definitely answer it. All right. So and now maybe you also talked about the solutions of the differential equations. Right. So can somebody confirm? So MH here is saying, is it just me or says breaking up? Oh, okay. So which means I'm fine from this end. So maybe you have you just have to sort out the network issues, or if you move to a place where there is enough connection. All right. So now what we are faced with now is Now that we know about these the differential equations, how do we solve them? Okay, do solutions of these differential equations exist in the first place? And if they exist, can we solve them explicitly? Can we find the exact solution of that differential equation? So yes, you had your differential equation. Maybe let me share the whiteboard here. You had a differential equation of the form dy dx is equal to f of xy in general. And then for existence and uniqueness of solutions, for existence and uniqueness of solutions, you require that f there, that function f of xy should be continuous. And then you require that the partial derivative of f with respect to y should also be continuous. So when these two are there, are satisfied, then you know that you have existence and uniqueness of solutions. And of course, now the question is, yeah, solutions exist. All right. So we deal with existence here. The solutions exist. So it's one thing to know that they exist. It's another thing to find them. How do you find them? Okay, am I moving a bit fast? All right, so I will, so yes, no, yes, no. So let me slow down, but keep on reminding me. If you are talking about what is happening on this whiteboard, don't worry about that. We haven't started what we are doing today. I'm just giving you a background. But of course, this is being recorded, and a video, the compressed video, will be uploaded online so that you will have access to it. Okay. So the question is, if solutions are existing, how do we find them? That's the first question. And then, is it possible Okay, yeah, the questions you're asking, I will answer them as we go. Thank you. So is it possible to get exact solutions? Is it possible to get exact solutions? So here you can have a yes or a no. If it's a yes, then celebrate, you are done. If it's a no, so how do we visualize these solutions? If it's a no, how do we visualize this solution? We know that they exist, but we can't find them in the exact solutions. So how do we visualize these solutions? Can we determine the nature of the curves of these solutions without knowing the solutions? So the question is, yes, we can visualize these solutions. And what do we use to visualize these solutions? We now use what we are doing today. That is what? That is the direction fields. So we now use the direction fields, or they call them direction slopes. When we are basically talking of slopes, we are talking of some tangents of some sort. related to some tangents of some sort. So we are now going to use direction fields to get the graphs of solutions for a solution that we don't know exactly, but we will know how the graphs will look like. So that's the whole idea of direction fields. Where we don't know the solution exactly, we can determine how the solution looks like, how the solution behaves at a particular point, how the solution behave when we reach infinity and minus infinity, which we call the long-term behavior. So today's lecture is all about determining the nature of solution curves for solutions that we don't know explicitly, but we know they exist by just using the qualitative features of the differential equation. In other words, we don't need to solve the differential equation by integrating, but we can use the derivative itself to determine how solutions behave. So that's once you get that idea, to say we don't solve the differential equation, but we can use the derivative to determine how the solutions behave and even draw the curves qualitatively. Basically, we're just saying we will know that this is the nature of the curves. They are bending inwards, outwards, and these like this, like this, like this, by just knowing what the derivative is at a particular point. So that's what we're going to do. And we're going to do that in three ways. And let me go back to the materials there. Let's hope I will get this one back. Yes. Yeah. So there we are. So that's why we need direction fields. So the question is, what are direction fields? And what do they tell us about the differential equation? So this is just differential equation, short for differential equation. What do they tell us about the differential equation and its solution? So basically, we're just saying, can we sketch the solution curves of this problem without knowing the solution, the exact solutions? So these solutions just referring to the exact solutions. Can we sketch the solution curves without knowing the exact solution? And then if we can do that, can we also establish the behavior of these solutions, the solution curves? So these solutions are now referring to the solution curves near a point or at plus or minus infinity, where we talk about the long-term behavior. So this is what we are going to emphasize on around this solution curves. If we understand this definition and what the direction fields does to us understanding, towards us understanding the solution and this behavior, then we are done. And then the next thing is to say, for those problems that we can solve exactly, which methods are we going to use? And then that's when we talk about the separation of variables. All right, so let's, this is just a very casual definition of a direction field. So this is a set of line elements. So you are just drawing lines. Line elements, you're just drawing lines. These are lines drawn at every point xy of the with a slope f of xy if we consider the differential equation, which is the first order differential equation. Okay, already if we are talking of f of xy, already f of xy is representing the derivative. So the derivative represents the slope. So that's why we can call these direction fields or direction slopes. So the direction there is just telling you that this is the orientation of the derivative. Is it horizontal? Is it vertical? Is it slanting? So So those are so we will have the orientation. So the orientation of the slopes So you can have a vertical orientation, you can have a slanting orientation. It could be slanting this way or that way. Okay, we just put arrows here just to, or we can have a horizontal orientation. So at every other point XY that is specified in a given region, so this region could be a small rectangle or the whole of the XY plane. So you are only trying to check at, for example, the point 1, 2. What orientation do we have there, given the function f xy? And of course, here, this is where so I took a grid where x is 1, 2, 3, y is 1, 2, 3. And you can see here that at every point, that dot in the grid, I have some example of orientation given there. There's some orientation given. So here is a bit slanting, 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 slanting. But you can also have, if I am to add some here, I can have a horizontal orientation. I can also have a vertical orientation. So now all you know is the graph. These are slopes, by the way. These are slopes. So all you know is the graph of the solution y here is going to come and touch the tangent, these small tangents. So when you put that orientation, you are actually drawing some small tangents at the given points. So the graph will definitely just touch the tangents, and then probably it will be moving like that, something like that. So you will know without finding the exact solution how the solution behaves and where the solution, the orientation of the solution, the qualitative features of the solution actually. So that's yes.
Sir,
Yes.
so I would say for a situation whereby you get the gradient is undefined or is horizontal. Let's say it's undefined. How would you know it's going up or down? I see that you drawn a vertical line there. So how do you know that it's going up or down?
Okay. Do you mind waiting 2 minutes?
Yeah, I
Then
can wait.
you ask this question if I don't answer it, because it's part of what I'm going to emphasize also in one of the examples.
Okay.
Yeah. So you are Mulele.
Yes, sir.
Okay, you can lower your hand now. It's fine. Thanks for the question. I'll address it. All right. So there we are. We have now known what direction fields are and how we can draw them just by an example that does not have any differential equations in mind. It is just an example, a visualization, a geometric representation of the direction field. So how do we draw the direction fields? So we have 3 ways that we can draw the direction fields. One is using points on a rectangular grid. So by saying rectangular grid, we are just saying on the XY plane, we just define a specific region where the solutions will exist. A, B, C, D. So that's the rectangle that we are talking about. So now we are given the differential equation, and we now know that our f of xy is just 1 over y squared. So the question here says, draw a direction field for the differential equation at the 9 point xy, okay, for x, y equal to minus 1, 0, 1. So basically here it says x is equals to minus 1, 0, 1, and y here is equals to minus 1, 0, 1. So what we are saying is, can make a combination on the grid, a combination of these points on the grid and came up with 9 points. Where was I not clear? Miss Q, Miss Q, I'll call you Miss Q. Do you mind? Do you mind talking through the microphone if you can, Miss Q? Okay, the rectangular grid. All right, let me, okay, now don't worry. I'm getting there now. All right. So let me go to the whiteboard. So we have our XY plane, right? So we then say we want to define Y to be an element of okay, no, that's fine. To be an element of C and D, and X to be an element of A, B. So what we are going to do is to just say, um, what we're going to do is, can we draw these regions here on the XY plane? So yes, our A there, our B there, and then yes, our C here, our D there. Now the region that this cover is what we call, is actually a rectangle, right? So the rectangle has points, so we can define points on the rectangle. So, and then we specify, these are the points that we want to define on the rectangle. So when we subdivide this rectangle into these small points that are in and on the rectangle, what we form here is actually a grid. So in other words, we will evaluate F at each point there. Oh, this whiteboard is it just disappeared here. All right, let me see if I can. So I was now showing you the rectangle, and we put some points on the rectangle. So the set of these points on the rectangle is what we call a grid. The set of these points on the rectangle is what we call the grid. Okay. So what we were going to do is to evaluate F at each point there. We evaluate the values of F, So this could be 1, 2, 3, 4, 5, 6, F7, F8, F9. But remember, dy dx is equals this F. So by evaluating F at this, we are actually getting the values of the slope at each point, at each grid point. So the whole rectangle divided into points is called a grid. And then the small point there, just one point, is called a grid point. All right, you'll meet this language in APM2B as well when you do numerical analysis. All right, so that's basically what we are to be referring to as the grid. So now let's go back and look at our example. So it says using defined points on a rectangular grid. So I was saying you have your grid, all right? You have your grid for x, y. So you can see x starts from -1, 0 to 1, and y -1, 0, 1. And then we have 9 points on the grid where we have points -1, -1, -1, 0, -1, 1, and then you have 0, 0, -1. Where is it now? -1, -1, minus 1, 0. Okay, minus 1, 0, minus 1, 1. And then we have the other one minus 0 minus 1, 0, 0. And then we have 1, 1, 1. And then with the other 3. So I said finish up here. You can see the other 3 is minus 1, 1 minus 1, 1, 0, 1, 1. Those are the 3 left. Okay, so now here we are, we have the grid first. That's the grid. We have managed to get the grid points, 9 of them. And the question is, now let's find the value of the derivative. Remember, this is 1 over y squared. So in other words, on a point minus 1 minus 1, the derivative is defined by the value of y there. So you substitute y is equals to minus 1 here. You get to minus 1 squared is 1, and then the derivative is 1. So if the derivative is 1, you just have to go, and it means you have moved 1 in this direction and 1 in that direction. So it has to look like this. This is the orientation of it. So it cuts the corner of where the two lines, the horizontal and the vertical line, meet into two halves, which means, I mean, by 45 degrees. So that's this is your dy dx is equals to 1. So we go to that point minus 1 minus 1, and our orientation, you can see, assume you had drawn perpendicular lines there, and then you draw a line that is 45 degrees, divide that angle into 2, then you have your orientation. But because this is positive, so positive orientations will move from left to right. Okay, from bottom left to top right. So that's why we have this orientation here. That's why we have this orientation there. Then we go to minus 1, 0. Minus 1, 0, it means substitute the derivative when y is equal to 0. Let me see. Yes, I should go back to where we substitute the y value. Maybe let me go back. Let me go back through the whiteboard. So we have dy dx is equal to 1 over y squared, and our grid point is minus 1 minus 1. Now this means x is equals to 1 and y is equals to minus 1. So we are just saying find the slope of this function when x is equals to minus 1 and y is equals to minus 1. This is just equal to 1 over, but we don't have x, so we don't have to worry about the x coordinate here. So what we worry about is the y coordinate. So this is minus 1 squared, which is 1. So we are saying the slope is 1. So we know the slope is distance. So we are at this point here. We want to get the orientation. So when we have a positive slope greater than 0, we always have these orientations that are moving from left to right. When we have the negative slope, then we have these orientations here from the top left to bottom right. Okay, so this is the negative orientation. So here we have 1, that's the slope. So it means we move increase in y over increase in x. That's one movement in this direction and one movement in that direction. So this is how the line should look like. So we are moving, because it's positive, we are moving from bottom left to top right, because we have a positive positive derivative. But of course, we now need to check how is the orientation going to be like. So for example, if dy dx is equals to 2, it means movement in the y is 2 and movement in the x is 1. So you are going to have on a scale that is well calibrated, 1, 2. So yeah, so you have 1 movement in the x and 2 movements in the y. So you can see it is still bottom left to top right, but it's no longer, as it doesn't look anymore like the what, the slope 1. So it's inclining towards the y variable more than the x variable, because we are moving more in the y direction than in the x. So this is where the difference is. This is how you determine the orientation at every point. So now I'm going back. So where we have 1, yes, I think I indicated that what you get here is the points of emphasis. You still get these together with the recording, so don't worry. It's the same thing, except that when I explain here with certain examples, I'm emphasizing what you are going to get there. So there you have more and more, you have a different example to this one. It was dy dx is equals minus 0.2 xy. So it has a different orientation together. So you have now 2 examples that you can deal with from the notes and from this lecture. So I do that. I will, when I emphasize, I don't want to repeat what is in the notes, because sometimes you are bored to just see the same thing that you read before. So this is just to give you another flavor of the same thing. Yes, I'm going there, Abdul. I was still explaining about the question. I was answering the questions there on orientation. So I'm now going there. So now we go to the point minus 1, 0. So in this point, y is equal to 0. So 1 over 0, that's where we have our infinity there, undefined. So when it's undefined, that's where we have a positive orientation. It means when it's undefined, when the slope is undefined, it means the movement in the x direction is 0. So we have a vertical asymptote there. So we have a vertical asymptote. So that's why we have a vertical orientation there. So that's why you get this vertical orientation, because the derivative is undefined. So the slope is undefined where we have asymptotes, and the asymptotes are vertical lines. So they also determine the orient. So they have a vertical orientation at that point. And then if we substitute at the next point, you will find that the slopes at every other point except when y is equal to 0, they are all vertical. I mean, they are all oriented from left to right, and with slope 1. They all have slope 1. So that's why now you can see where y is 0 is on the x-axis here. At the 3 points that are on the x-axis, y is 0. So I mean, the derivative is 0, sorry. So and y is 0 anyway. So we basically have vertical orientation. But on all others, the derivatives are just equal to 1. And we have that the bottom left, top right, bottom left, top right, bottom left, top right orientation. So what we have now on this grid, now is what we call the direction field. So this is the set of lines that show the orientation of the slope of the slope function f at every specified point xy. And now the question is, how do you then come up with the probable curve, the curve that represents the curve of the solution? So you can see, because we always touch these tangent lines. These orientations arrows are actually tangent lines. So we basically now have to touch them when we draw the curve. It's not a straight arrow. What do you mean by it's not a straight arrow? This is a vertical arrow. Can you see this? If I go back at 0, 0, look at 0, 0 here. Can you see that it's a vertical line? Unless if I don't understand your question, but this is, I can see a vertical line. Can somebody confirm that is a vertical line there? On the table, oh, sorry. All right, that's a mistake. All right, thanks for that. This one is not supposed to be like this. That was an error. It was just an error in putting the orientations. But of course, if it's undefined, it has to. How do you know if it's upwards or downwards? If the slope is, oh, okay. All right, you can forget about the arrows going. Okay, let me answer it in two ways. So how do you know if the line is upwards or downwards or sideways? All right, this is what I was explaining. For the value of the slope here, 1 is positive. So all positive slopes will have bottom left, top right, but how they look like depends on the value of the slope. So if for example the slope was 36, then it means I have to move just 1 in there and then 36 in this direction. So it will just be almost straight. But if it's 1, it goes there. This is for 1. For 2, is somewhere there. So how the orientation looks like depends on the value of the derivative. Now, if for example I had dy dx is equals to -1 at a point, if the slope was -1, then obviously I will have now an orientation that goes from the top left to the bottom right, because I am moving -1 in the y direction and 1 in the x direction. So I go down -1 and go 1 direction, the positive direction in the x-axis. So you now have the top to left, the top left to right bottom. All right. By integrating the second column, what do you mean? Do you want to integrate the second column? The second column, you want to integrate. Oh, so let me try to get you. You want to integrate the second column means dy. Yes, can you talk? You want to talk? Okay. So the moment you start integrating the first derivative there, the moment you want to integrate, it means you can find the solution. But we are saying for direction fields, they are mostly used when you can't even integrate to find the solution. So forget about integrating, but if you're integrating, then you are going to get a solution, but not the direction fields. The direction fields, they only use the derivative. They use slopes. So forget about integrating. You're only going to substitute the value of the derivative at a given point. Yes, you are going. That's the second. Remember, I said I have 3 ways of doing this. So the borrow, wait a bit. within our next example will answer your question. All right. So there we are. We have our direction slope, and of course, all you do is to draw a curve that touches the slope, that orientation slope or the orientation line. Of course, you want to touch. All right, so you are just touching. So you have a family of solutions which will behave like this. A family of solutions that will behave like that. So what you now need to know is which one am I interested in? Then I say y of 1 is equals to 2. So then I'm just saying I want this curve to go through the point 1, 2. Then I'll single out one of them, probably it will be this one. This will be the curve that I'm looking for. So depending on what the shape of the curve. So you are connecting these gradients, these slopes, these orientations that you have done. Remember, okay, I'll explain further later, but because we are just having very spaced, these grid points are very spaced, so we can't. It's kind of difficult to see, but you will see with the next two examples. And okay, Mashaba, and you then understand how you get those curves. Yes, Mashaba.
Hi, sir. I'd just like to know, whenever the gradient is undefined, will the slope always be pointing upwards?
Yes, it's vertical. Remember, when the gradient is not defined, it means we have an asymptote, a vertical asymptote.
Oh, okay. Thank you.
Yes. Yeah. Okay. Welcome. So in this case, for this example, Nondiza, the divided the x term is only in terms of y, but the ones that you see later, they are a mixture of x and y. So hang in there, and you will see different examples that will then give you a better coverage of the different combinations that you can get. We are going to work on an initial value problem. Don't worry, we are going to work on it. We are going to work on it. So M Saba, yes, Como. Yes, please, Como. So what does the divide x mean? That's a slope. So our differential equation, the first order differential equation, is actually a slope equation. So that's why we concentrate on the right hand side. F on the right hand side represents the slope of a function at every given point. All right, you were answering. Oh, okay. All right. So okay, that's fine. Thank you very much. You were just telling your colleague that the derivative there is a function that gives slopes. Thank you very much. I appreciate that contribution. All right, let's move on. Now, we move on from just a defined grid set of points. So now we are now looking at nuclines. So we can draw the direction fields using nuclines. What are nuclines? These are a set of points where the derivative is 0. The derivative is 0. So when the derivative is 0, we have a horizontal orientation. The 0 derivative is horizontal. Okay. So when we deal with nucleus, it will still, okay, if you have that one at 0, it will still upwards, doesn't matter. So don't worry about those arrows. You can still draw those lines without arrows. The orientation is just bottom left to top right, or bottom top right, bottom left, or just horizontal. So you can still do it with just putting these slopes like this without putting arrows. So it will still work. So the arrows is just saying there is a direction, vertical direction, or slanted direction, or going from top left to bottom right, or top right to bottom left, or horizontal direction. So you can still use these without the arrows. But for example, if we were talking of the velocity function, then with the velocity function, it has a direction. That's why we will then use arrows. So the arrows is just a default way of saying these differential equations have practical applications in real life. So when you see that arrow, don't be, there is nothing, even if you do this, even if you do this, there is nothing that will change. You will know that the curve will just touch the way it touches is the same. It doesn't matter where. It depends on where you're coming from in terms of the initial conditions. It only depends on the initial conditions. But how you touch, you can touch from inside or from out, from the opposite side, depending on the initial conditions that are specified on the problem. So don't worry about arrows there. Wouldn't the what? Yes. So yes, you are right, but you can't have. Tell me, what if you do this arrow here? What will be the derivative? What will be the sign of the derivative if you then look at that as direction? Would you say this is less than 0? No, because the less than 0 is top right, bottom left. So you can use this without mentioning, without focusing on the direction of the arrows. But when we talk of practical questions, like for example velocity, you would know that if we want arrows, we only have the bottom up and then the bottom left top to top right, or top right to bottom left, if we are talking about arrows. Okay, so basically, don't be confused by the arrows. Just look at the orientation. The orientation, that's what is important. But arrows are just nice. They will tell you what is happening. They just sort of give you an idea of how you are going to draw the graph anyway. So don't be confused by arrows. Now we're defining clients here. All points where the derivative is equal to 0. This is where you get your fixed points, your equilibrium points, your stationary points, and stuff like that. Those are called clients if you're dealing with differential equations. So how do you draw the direction fields of this differential equation? So you now want to find they'll give you an idea of what is happening. So at clients, if your solutions hit a client, it stays there. If a solution hit a client, it will stay there forever. Or it will not be even allowed to hit the client, depending on whether the client is attracting or repelling. All right, and how do you know it's repelling or attracting? You will see with the orientation of the what? Of the curves. All right. So let's see. Let's find our clients. So our clients, after solving, you factorize here, you get y equals minus 1, 1, and 2. So you go to your graph. Y is equals to minus 1 is this red, the lower red dashed line, and then y is equals to 1, the middle red, and then the y is equals to the upper red. So now, by having these 3 lines, what did they do, these 3 lines? These 3 lines, y is equals to minus 1, y is equals to 1, and y is equals to 2. Now, let's look at the values of y. They run, so here we have 0. So they run from minus infinity to infinity. So what did we do by introducing these null-clients? We have subdivided this region into the region where y is less than -1. And in this region, the graph has a cell orientation in terms of the derivatives. So this is the case where you're not given grid points. So you now have to look at the whole entire region. And the beauty of the null-clients is it will subdivide the entire region for y into small sub-regions, where in this one region, before we reach the first null-client, the behavior is the same. The behavior of the solution is the same. In other words, the derivative here is the same. The derivative is the same. The value and sign of the sign of the derivative is the same. So the derivative sign is the same, whether it's positive or negative. So if we just found that for at one point in this region, the derivative is negative, we know that the derivative is negative throughout the rest of y of the region y is less than -1. And then we have the next region where y is in between 1 and -1. The behavior of the solutions is similar. The sign of the derivative is the same. And then we have 1 less than y less than 2. The sign of the derivative is the same in that region. And then we have y greater than 2. And then you can see we have, by just introducing null-clients, the three null-clients, they have subdivided the region of values for y from -infinity to infinity into 4 sub-regions. So what we want to do now is to check what is the sign of the derivative inside those in sub-intervals. All we know here is at the null-clients, we have the derivative is 0. At the null-clients, the derivative is 0. So at all the null-clients, the derivative is 0. So we want to now check what is the behavior here, what is the behavior here, what is the behavior of solutions in terms of the signs of the derivatives. All right. So how do you do it? Because we know that in the entire sub-region, the behavior is the same. So you just choose a candidate in between, a candidate value of y. So for example, between -infinity to -1, I can just check at -2 or -3. It doesn't matter. You choose a value that makes your computation of the derivative much easier. Here I'll just choose y is equal to 0. Here I'll just choose y is equals to 3/2. Here I'll just choose y is equals to 3. So all I now do now is take y is equals to 3, go back into the derivative on the right hand side, substitute y is equals to 3. What is the value of the derivative at that point? And then I find that it's equal to 16, I think. So at y is equals to 3, y dx at y is equals to 3 is going to be equal to 16. So 16 is a bit steep. Okay, I'm going back now to my so all I did now is I chose y is equals to 3 here in green. The green font shows that the derivative is equals to 16. So 16 is a bit steep. So you are just saying I am moving 1 here and I'm moving about 16. So it's sort of a bit steep orientation. Okay, it's supposed to be very steep. Okay, and then I go to y is equals 3/2 is somewhere here, and then you see it's -0.3.1. So it's not really much sharp. So it's more like close to 0. So the orientation from top left, right, bottom right, from top left to bottom right is just a little bit flat at that point. So I know the orientation is negative there, the negative orientation. But the value also tells me that at this line here, y is equals 3/2. I have a very flat orientation from top right, left to bottom right. And then I come here, I choose y is equal to 0. Then I see that I get -2. So I have moved -2. So it's more inclined towards the y-axis at every point. So that's -2. It just gives me a rough idea of how it should look like. And then I come to y is equals -2 here. Then I get 36. This is very steep. It's positive and very steep. Now I'm here at y is equals -2. But I know that by the time I reach y is equals to 1, the derivative is equal to 0. So I'm starting with a very steep orientation when I'm at y is equals -2. But by the time I am at y is equals to 1, I am now having a horizontal orientation, which means the orientation is changing from steep to slightly flat slowly until it becomes flat at the outline. So then that's when I will know that my curve will have to behave like that, because I now know the derivative at this point, and I know the behavior of the function in that from that point to the outline. I'm from the steep 36 there, but by the time I'm at -2 here, by the time I hit -1, I should be flat. So I will not lose the orientation, but I would then just flatten. By the time I reach the outline, I'm now flat. So then I can now know that the behavior of the solution behaves like that. All right. I think there's a question somewhere. Hey, don't worry about assessment, worry about understanding, okay? So I'm not going to answer that one. The questioning will come in different ways. You will find that the direction fields will be combined with methods of solutions of that. So don't worry about assessment for now. You worry about understanding. Okay. So you see, if you have a habit of just learning to get marks and how much percentage, which is the mentality that is coming from somewhere I don't know, you will not understand. So I teach people to understand. Okay, I'm moving at that speed of a light. Oh, sorry, I'll slow down. I'll slow down. All right. Yes, you will pass. If you understand, you will pass. Don't worry, Kasim. Understand, and any question that comes, you punch and you get the marks. So it doesn't matter how much marks. I can give you 30 marks on the direction field. If you understand, you get all the 30 marks. I can give you five marks, and it's out of 10. And if you don't understand, you will still lose those 5 marks. Oh, welcome, Kasim. That's the route I went through. You will get it. Understand, and you will get it. You want a PhD. All right, so there we are. Now all I know is now we have to draw. I only follow these, and also when these solutions now all will end up at the what? At the outline. The solutions will end up at the outline. The solutions will end up at the outline, going and going and going. So this is the behavior of the solutions on that. Oops. All right. I have shown you something that you were not supposed to see. All right. Sorry. If you are being kicked out, this is we can understand this through the videos that we are going to upload. So I'm going to do pre-recording of videos explaining the same things, and this video again is going to be uploaded. Okay, so don't worry. Let's move on. All right, so there we are. Now, where is the application now? All right, share the application. I want this. Where is it? Okay, so let me share. Okay, some are even indicating that we have to focus. That's fine. So here we are running away from the now client there, and then we go steep a little bit and end up with this now client. Go steep a little bit, and so we will go steep a little bit and flatten out, and we go. So the solutions will definitely come down like that, come down like that, come down like that. And of course, here we are running away from this now client, but we are going there on a very slanted, it's slow growth, slowly decreasing until we get to the now client itself. Okay. This one is a bit steep, so we are going to see the solutions behaving in this manner. So this is now the solution curves of that differential equation that we don't know its solution. I mean, you could solve this one using partial fraction decomposition methods, but the solution will definitely not be as easy to draw the graphs as you will see here when you use now clients. So this is how it's going to look. And then the question is, what is the long-term behavior? Yeah. Yeah. You can see because waves are just solutions, right? So now clients can basically give you an idea for how the caves are behaving also. Emphasis.
I
Talk
say.
to me. Yes.
Sir, can you please go up where we're given the equation of y?
Yes.
Yes. So I understand for null claims, let's say, we have to like find the sub intervals, the
Solutions.
isn't it?
The zeros, yes, or the root of that right hand side, yes.
So now say, how do you find the dy dx from that equation?
The dy dx from that equation, which one? This one.
How do you find the dy
dx is already defined. Look, the dy dx is what is on the right hand side, so you don't have to find it, it's given.
Okay.
So now all you do now is when you choose y is equals to 3,
Okay.
you just say y dx at y is equals to 3 is just
you see the
3 squared minus 3 minus 2 into 1 minus 3 squared, and then you find your value there.
Okay.
Yeah, the same way we were doing when we're doing with the first. When you substitute, you just substitute on the right hand side because that's what represents the derivative.
Okay.
Okay, welcome. Let's move on. Yes, let's move and see. So we are done with now clients here. They have given us our we have the solution curve. Now what we want to know is the long-term behavior as x approaches infinity. So this is the direction of x approaching infinity. So let's say we have taken the initial condition. Y of 0 there is the initial condition. Is there somebody who wants to talk, or they just left? All right, that's fine. So there we are. We are having an initial condition in this region. So we have y naught is in this region. Okay. So y of 0 is in this region. So for example, you can take y of 0 is equals to minus 3. So if you look at the solutions that start in that region, as x approaches infinity, where do they go? So you can see the red solutions, they always end up on the null line, y is equals to 1. So y will definitely approach -1. As x goes to infinity, as you go to infinity, you just see these solutions are just ending at that point. Now let's look at an initial condition chosen from this region. Say y of 0 is equals to, y of 0 is equals to 0. So you see that all solutions in this region are going down towards the same null line. So as you start in that region, all solutions are just going to -1. Now let's start solutions in this region. Y of 0 is equals 3/2, and then you find that all the solutions in that region are coming back to this null line, y is equals to 1. So as x approaches infinity, y approaches 1. And then when you then look at these ones in the other region, maybe y of 0 is equals to 4, you then see that all solutions are going up. They're going up. So then in this case, y is going to approach infinity. So that's the long-term behavior of the solutions. This is the long-term behavior of the solutions. Now, you have not found the exact solution, but you can see how much you can answer by just using direction field. So on to y prime. You substitute y into, this is the value of y and x into y prime. But the y prime is the right-hand side. Okay. So you just look at the function on the right-hand side of the derivative. Yeah? And whatever is there, x, put a value there, put y value there. And so you have already substituted into the derivative. So what is on the right-hand side is a function which defines the derivative. That's where you substitute the values of x and y at any given point. But in this case, we only have a function that is in terms of y. So you are just substituting y. But in the first one, we had grid points of x and y. But of course, lucky enough, we had only y there. But if you look in the notes, you find that the function was defined in terms of x and y. So you would have to use the values of x and the values of y to substitute into the right-hand side function. All right, let me move now to the isoclines. Now, on isoclines, these are the set of points for which the derivative is constant. So if you look at it, now clients, we just said the constant, let's call the constant c is equal to 0, which means we have a horizontal orientation. So with isoclines, these are more generalized. If c is not equal to 0, c can be equal to 1, c can be equal to 2, c can be equal to -1, and so forth and so forth. So when you have that, then you have what is called an isocline. Abdul?
Sir, can you please go up to the long-term behavior?
Yes, I'm there.
Yeah, can you please, no, I'm just looking at the example also on the slides. When we looked at the long-term behavior for that example, the y's were different. Like it was -1, yeah, it was 1 and then 2. It's different on the slides. So is that a mistake or what?
Where exactly? Here.
No, on the slides on Blackboard.
On Blackboard, on this particular example.
Yeah, so this example.
All right. I will have to check that and come back to you.
Okay.
Right. Okay, let me just check. I think I have it. Just a moment. Yes. Mistakes can happen. Which one is that? On the same example. All right. So this is the same example. Aha. So there is no mistake there. there is no mistake there. So, all right. So what is happening here? Do you see this? Is it sharing? Yes. All right. So you see. So here we covered y is less than 1. In fact, it was supposed to be, all right, minus 1. Minus 1 less than, okay. So it's just this part here. Minus 1 less than y less than 0, 1 less than 2. So the other one was supposed to be, oh, all right, all right. Then we have this. Ah, no, that's the thing. You see what is happening here? Y of 0 is equals to 2 already because we are at the nucline. Y of 0, remember y is equals to 2 is a nucline. And I said all solutions that hit the nucline will not leave it. So if you start on the nucline, you remain there for life. So this is okay. And then y greater than 2, then this is where we chose y of 0 is equals to 4. And we saw y is going. So what is just not in here is exhaustive representation of the intervals. For example, y is less than minus 1 is not there. But here I was trying to show you that if you are not on the nucline, you will go to the nucline or move away from the nucline. There's a certain nucline you are going to approach, but you may not even approach any nucline. But if you start at a nucline, like in this case, you basically end up at the nucline. You remain there for life. So that's what I was trying to. So there is no mistake here. Everything is fine, except that what I'm using now here is exhaustive representation of all the regions, and I'm looking for long-term behavior in all the regions. But I can ask you from one region without looking at all the regions. It doesn't matter. So it doesn't mean that I'll ask you all long-term behaviors in all the regions. I'll just pick one of interest. And then it's up to you now to go and pick and test and see after drawing these solution curves. All right. Now let's go to isoclines. Look, these are the set of what the derivatives are constant. So these now, so the anoclines are actually a special type of isoclines. So we are just saying a f of x, y, remember with dy dx is equal to 0. So f of x, y should just be equated to a constant value c. And of course, c is an element of real numbers, which means it can take any value, 0, 1, 2, minus 1, and even the decimals, it can. So with this particular equation, we have y plus minus x is equal to c. Those are the isoclines. So we now have to draw isoclines by just picking the some certain values of c. But of course, make sure that you also include the nuclines because they have a special character of solutions that hit them remains where they are. So so we picked here. Remember, c here is representing the slope. So we are picking a slope minus 1, minus 2, 0, 1, 2. And then I have now the lines that defines solutions, the set of solutions that satisfy this c is equals minus 2. So I just put minus 2 there and make y sub with the formula. Then I have a line here. I do the same, I do the same, I do the same, I do the same. So all I do is to draw these graphs. So this one is y is equals to x because c is equal to 0. This one is y is equals to x plus 1 because c is equals to 1. This one is y is equals to x plus 2 because c is equals plus. Then this one is x minus 1. This one is x minus 2. All right, so there we are. What do we do? There's a question. No, you are not given. You are the ones to experiment with it. So this is not given. You experiment it, but make sure that you also include c is equal to 0 because it has a special character in terms of the behavior of solutions when the derivative is equal to 0. So you can choose conveniently. So you can choose more. You can c is equals minus 3, c is equals to 3, just to see what will happen at those now clients. Now, yes. Yes. Choose values that are convenient in terms of you being able to draw those isoclines. So you choose a convenient value of variable c. Okay. So now what is happening? I'm not sure if you can see this. Now let me drop this. I think I have another nice. I want to take is it? Yes. So I'm sharing this. This will be nice for me. So now I have my now clients, and I'm going to draw them in colors. So I have this, I have that one, I have that one, I have that one, I have that one. All right. So I know here c is equals to 0, c is equals to 1, c is equals to 2, c is equals to minus 1, c is equals to minus 2. So what it means is, it means the slope here is 2. The slope here, yes, is there a question? The slope here is 0. The slope here is 1. The slope here is 2. So what do I do? Along this now isocline here. So somebody's, yes, you want to ask? All right. So if you're not asking,
it was a mistake.
no, that's fine. That's fine. Just mute your mic. It's fine. Right. So what we know is the slope c is equal to 0. It means I have a horizontal slope along that line, along that isocline. So this the isocline y is equal to x. Along this isocline, I should have the slope, the horizontal orientation. So along this isocline, I will draw. This is how the orientation is. I have a horizontal, so I put horizontal arrows along that line, that isocline. Along this isocline, the slope is minus 1, so I have this orientation here. That's the minus 1. Then along this is minus 2, so it's a bit sort of going towards the y-axis. So I have a slightly different orientation. All right. So I have these 3 isoclines. Then let me go to the slope equal to 1. Along this isocline, I have a slope that is equal to 1. So you will see that the slope is exactly with the same orientation as the isocline. So that's the slope equal to 1 there. But then along this isocline, I have the slope that is now a little bit off, going to 2 there. Now, here is the thing. If you, what it means here, if you hit, yes, you can't see anything anymore. All right. The board, oh, it's gone. Sorry. Right, you can see now, right? Let me see. Yes, I can see, you can see. Thank you. Right, so now there we are. I will sort of, yeah. So there we are. We have our board. So what it means is solutions that start solutions that are on this isocline of slope c is equal to 1, they go through that isocline and remain there. Okay? But you see here it's 1. The slope is close to this is 1, but as we go towards this isocline y is equal to x, the slope is going to be 0. So you have a change of slope until it's horizontal. And then from here, you have a change of slope until it's -1 there. And you have a change of slope as you continue until it's -2 there. So you can now tell that these solutions will behave like that. So they start closer. If they are not on the isocline, they will start closer and move down like that. Here you can see you start with a slope 1, and by the time you reach this one, you are already at 2. So you are changing slightly. You are changing slightly towards the orientation 2. Then solutions will behave like that. That part. So the solutions will behave like that. If they don't start on this, they will behave like that. And then this now gives you the solution curves. So the isocline. So these are the two examples where you don't really need to know the grid points, but you just need to know to use nounclines or isoclines. So for nounclines problem, it was we were lucky because we didn't have any. We were lucky in the sense that we didn't have any. The whole differential equation was dependent on y only, specifically, explicitly. So it was what we call an autonomous differential equation: y squared minus y minus 2 into y minus y squared. It's basically solely in terms of y. So y squared minus y minus 2 into y minus 1 squared. All right. So you see here, we don't have any x value. There is no x component here. So when there is no, the differential equation is defined in this form, then you go for nounclines, because there is no way, there is no x values. So nounclines will work here. But the other one now as the y, the x is equals to y minus x. Now when we have x and y on the right hand side, so this one you can use the isoclines, because the x value here will then affect the behavior of the right hand side. So you then go for isoclines, but inside the isoclines you also have some nounclines there. So that's how you can tell when you're given a problem whether to use nounclines or isoclines. But in all these, you can also use the grid points if they are defined. In both of these, you can use the grid points. And of course, here, because nounclines are isoclines, you can also use isoclines. So wherever you're using nounclines only, you can also use isoclines, because the only isoclines you get there are basically the horizontal isoclines. They are horizontal lines. All right. So you can do that if you want, but this is just a simple trick that you can use. Yes, Fazwe.
Sorry, sir. Going back to isoclines, ne?
Mm.
So we were given the value of a straight line, isn't it? With a constant c. So we had to assume the value of c, isn't it? C is the element of real
Yes.
numbers.
Yeah, you choose. Yes.
So now we used the values of c to create the grids.
not there. We didn't create a grid there. You know, a grid should have specified points. But in this case, we didn't have specified points. We were just dealing with the isoclines.
But we used the value of C to draw the graphs, isn't it?
Yeah, C is not a grid point, is the slope. It is the slope of that line, that particular line.
Okay.
That particular isocline. So that is not a grid point. A grid point is a point of x and y. The coordinates x and y given it specified at any point. But C is just slope. So when we calculated dy dx at x is equals to at -1, we got the slope is equal to 1. That value 1 that we got as the slope is what C is representing here. But we would have to get the coordinates of x and y for us to get that C. But in this case, because you don't have the prescribed points x, y, you then now work from the top down. You now work with an assumed value of C to get the information about how the curve that is represented by this isocline.
Okay.
All right, so there we are. Let me look at before I go. Yes, can we stop here? Now I have to do you specify the methods to be used? Okay, how you will know? Well, let me go from the top. Wait a minute. Say if you go beyond C, then it will look like a circle. It wouldn't look like a circle. It will just be a curve because the negative orientation, the negative slope is always from top left to bottom right. You can't have top right to bottom left. You can't have that orientation. So it won't be a circle. How will you know when to use null class? I think I basically answered that. Do you specify the method? You have to know now. I gave you the 3 methods. It's your choice. Say, can we stop here? No, I cannot stop. Those who are seconded, you are overruled. So I have just one part, which is easier. I gave you examples, 3 examples so far. Go to the tutorials, you get more examples, and you are fine. So let me now go to the last part of it's hectic. Now through exercise, through practice, you will be fine. Don't worry. That's why we took our time to emphasize this. And we are still there. If you still, I'm not a politician, so we still are here to assist you. And when I now do the pre-recorded videos, I will also take all these questions into consideration in my explanations, and it will also become much more clear. So it's the first time you're introduced to it. We have been here since 2018. What are you still doing here when we were here in 2018, Lavender? It means there's a challenge there. Okay, don't use emojis. Somebody is being distracted there. So there. I want to know if a dependent variable is to a power greater than 1. Is it linear or not? All right, thanks, JV. Let me answer yours, then I go straight to the. All right, let me see. Are you seeing this, JV? So you have your differential equation, dy dx. So your question is, I want to know if a dependent variable is to a power greater than 1. Is it still linear or not? All right, let's go to the definition of a linear function. Now, definition of a linear function, a linear equation. 1, y and its derivative should be of degree 1. That's the first part. Second part, coefficients of y and its coefficients of y and its derivatives should be only in terms of the independent variable. If you look at this classification there, these two should be satisfied. So if I have dy dx plus 3x cubed y is equals to e to the power x. Now, let's check. The derivative is here. Is it of degree 1? Yes. Y is here. Is it of degree 1? Yes. This one is satisfied. The coefficient of y and dx. So the coefficient here is 1. The coefficient is 3x squared. And of course, the right-hand side plus the right-hand side function should only be in terms of the independent variables. So it is in terms of x solidly is fine. In terms of x solidly is fine. Then we are fine. It's linear. So it doesn't matter what power the independent variable has, as long as these two criteria of classifying a differential equation as linear are satisfied. That I am done. I don't know if I answered you, JV. Yes, so if I answered you, then I move on now to the separable equations. So now I want the separable equation. Oh, AB, I write the hieroglyphics. All right, I'll tell you when I'm. Let me finish for today's material. In 9 minutes, we will be done. So that you can be able to answer to go through your tutorial. So differential equations of the form dy dx is equals to g of x times h of x. So remember, this was f of xy. So now we can explicitly write f of xy as a product of functions of x only and a function of y only. So if we can do this to a differential equation, then we know that it's a separable equation. It means we can separate the variables x and the variables y in terms of functions. And also we will be able to separate the differentials dy and dx. So you can get this form or this other form here, or any other haphazard form that you can find, which you can play around and come to these two forms. So you can express any other haphazard forms into these two forms. They're equivalent. So then you have a separable equation. So what do you do now? You now multiply by dx throughout. So if you multiply by dx, you will cancel here and you have a dx on the right hand side. So on the left hand side we have dy. So it's it's a function in terms of y alone. But on the right hand side we also want to have only a function of x. So we are forced to take h of y to the left hand side. So then we have dy over h of y and g of x dx. So now when we look at this form now, we now have functions of y on the left hand side and functions of x on the right hand side only, not a mixture. And if you've done this, you have separated the variables, and our variables are what? X, y. So functions of y have been separated from functions of x. Then we have a separable equation. And then it's easy now to find the solution. We then integrate both sides. So integrate both sides. Integrate both sides. And of course, we have our mother-in-law there. We should not forget, because we're going to pay a lot of damages. So don't leave this mother-in-law here. All right. This is chapter 2. So after in chapter 2 you have direction fields, and you have separation of variables first, and then you go to linear equations, exact equations, chapter 2. All right, so C is our mother-in-law. We should not forget her. And if you leave that, is a punishable offense. So that's a constant of integration. All right. So now we have something that is haphazard here. Look, doesn't look well. So I know on the left-hand side, I have an opportunity of dividing by e to the power x and multiplying by dx, and I can take them to the right-hand side, fine. But on the right-hand side, I have a sum of e to the power y and something that doesn't look well there. So then I need to separate these variables. I now use properties of exponential functions, and then I have the power y there. Now I can see that I can factorize e to the power minus y. And now I have some form of product of function of y only and functions of x only. Once I've achieved that, I know I can divide and multiply. So the next thing is to divide by e to the power minus y and multiply by dx and divide by e to the power x. There we are. It's now a separated equation. And then now I can now see that e to the power minus y is just e to the power y. I de-integrate both sides. I simplified on the right-hand side. Integrate both sides. Those who wanted to integrate, this is where you can integrate, not on direction fields. So here we are integrating now. And use your integration by parts techniques, and of course, integration of exponential functions. And here it's impossible to find y explicitly as a subject of formula. So you leave it like that. But where possible, please leave it as subject of formula. And then this is a general formula, the general solution. Why? Because we have this C. Now this C is found when you specify the initial conditions. All right. Oh, we are ending now. I thought it's 150. It's fine. What will happen now is the rest of this, whatever I've given you right now is exactly what we need. The rest of this, you will find them on the pre-recorded videos. So I'll stop here, and the rest of this, we will not repeat this next week. We will go to the next. I owe you 2 minutes. This will be in 2 weeks' time. I'll give you your 2 minutes. Don't worry. But you know, when you owe me, I'll also take note of that. Okay. So sorry for going beyond by 2 minutes, but the rest of this you will see it. But it's all about separating variables, which is what I explained there, and the rest you can learn on your own. It's just integration. Now, even in the exams, you also owe me. Remember, when you come for marks, I would have given you more marks. And if you come looking for them, I'll definitely look for mine that I gave you for free. So we owe each other. We cancel those effects at some point. All right. So we'll see you in 2 weeks' time. Next week we will be with Dr. Visaya. All right. So thank you. Please don't be offended. We are just joking here, and it makes life lighter for us. If I manage to disappoint you, please forgive me. But I will always apologize for those mistakes that I intentionally commit. In the next 5 what? I will upload these videos tomorrow as promised. So I will not change that. I will upload tomorrow, so that by the time you do your official tutorials on Wednesday, you should be having your videos with you. Bye. I'm gone.